So there are some alternative axioms based on like bases and circuits. But let me remind you what those things are. So a basis for a matroid xi is a set B in I, which is maximal with respect to this property. So i.e., if I take B union X, it's not in I for any X that's not in B. Okay. And yeah, this word basis kind of relates to linear algebra, right? If I take a maximal set of independent vectors, that's a basis, right? And a circuit is a set that is not independent, so it's in the power set take away I, which is minimal with respect to this. So in other words, if I take away an element of C, it ends up being an independent set for all X and C. Okay. Okay, so one of the things we're going to do today is show that, so this is like defining a matroid in terms of its independent sets. And like we're going to also show that if it's convenient to do so, you can also define a matroid in terms of its bases or its circuits, and it all kind of they're all kind of equivalent. Before I do that, I should probably I'm going to need some other definitions, and also these show up on maybe your last assignment, so you're going to need to know about them. So the first thing is a concept, or the next thing I'll tell you about is the concept of the dual of a matroid. So the dual of a matroid, let's say the matroid is M, which is like X, I. So it's the matroid, so it's, well, actually maybe it's not clear so far that it's a matroid, but but it's the pair X comma, well, let's say M star, which is X comma I star, where I star is the set of all subsets of X that are disjoint from some basis of M. So such that there exists a basis of M, a basis B of M, such that Y is disjoint from B. Okay. Maybe let's think about this in the case of graphic matroids. So recall, for a graph G, the corresponding graphic matroid is the pair where like the ground set is the edges of G, and the independent sets are the subsets of the edges, such that the graph V of G S has no cycles. Okay, so yeah, this was the graphic matroid. So like this is my, like this is the set X in some sense, and this is like the collection of independent sets. Right, so let's just to make our lives easier, like suppose G is connected. Right, so then, then the independent sets correspond to spanning forests of G. The bases, so a basis, so the bases of this graphic matroid are the spanning trees. We saw that last time. Do we remember what were the circuits in this matroid? The minimal dependent sets? Yeah? Yep, exactly. Circuits are cycles. Right, you can think of that. Why are circuits, so why are the cycles, why is every cycle a circuit, for example? Like it's not independent because it has a cycle, right? Independent sets in this matroid are the things that don't have cycles. So cycles are dependent, and they're also minimally dependent because if I delete something from a cycle, I'll get a path, and then it's acyclic, right? And conversely, anything that's minimally dependent must be a cycle because, well, if it doesn't have any cycles, then it's independent. And then if it does have a cycle, well, if it has anything extra, like kind of hanging off of it, you would just delete it and it would stay dependent, right? What about, I don't know, like let's think about the dual of this matrix, or this matroid. So what would be a basis of the dual? They're kind of, I think it's kind of an awkward thing to talk about the bases, but of this thing, because so if you go back to the definition of a dual, right? Well, maybe we should start with the independent sets rather than the bases. So the independent sets of the dual of this thing. So if you just go to the definition of dual, right? A set will be independent here if there exists a basis of this matroid that's disjoint from it. Right? So an independent set here would be a set of edges, let's say S of edges, such that if I take G and I remove those edges, is connected. Right? Because it's like it's the sets of edges that are disjoint from at least one spanning tree. So it's like things that I could delete, and the graph stays connected. So then the bases would just be, oh, by the way, the dual of a graphic matroid is called a co-graphic matroid, so these come up sometimes. So it's perhaps worth knowing that terminology. And yeah, the bases, I guess, are just then complements of spanning trees, or like, yeah, sets S such that G take away S is a spanning tree, the circuits are kind of interesting. This kind of connects to some stuff we've done earlier in the course. So maybe have a think about it. What's going to be a circuit in the dual of a graphic matroid? Matroids are sometimes kind of annoying because there's like so many definitions layered on top of each other, right? It's kind of hard to see. But okay, what about a dependent set? So right, an independent set is a graph when I delete the edges. Sorry, it's a set of edges where if I delete them, it stays connected, right? So I guess a dependent set would be a set of edges that when I delete it, it's not connected, right? So if these are your independent sets, a dependent set would be a set of edges. You delete it, it makes the graph disconnected, right? So yeah, anyways, the circuits are going to be like the minimal sets with that property. That they literally just, you know, these are basically the kind of edge cuts. So kind of like from the max cut min flow theorem and things like that. So it's like, so sets of edges, you know, so a circuit would be a set S of edges obtained by partitioning I guess the vertices into sets like, let's say, A and B, and taking all the edges from A and B, from A to B. Well, am I getting this right? I don't know. I mean, you also want this to be a minimal edge cut, so I think I may have this slightly wrong because you want to take, I think you want that the sets induced by A and B are still connected as well. Because, yeah, I don't know, if my graph was like this, just a star, like every edge is going to disconnect the graph. So I think my circuits will just be like, this is a circuit, like each edge individually is a circuit, but if I made this my set A and this my set B, that would be a dependent set of edges, but it wouldn't be a circuit because it's not minimal. So I think you, need an additional assumption that such that, like, the graphs induced by A and B are each individually connected. Okay, I didn't actually think about this much before before doing this, so, but I think that's kind of the idea. Anyway, it's maybe I should just say it's minimal edge cuts. Okay. Okay. A few more little definitions. So with the Matroid, you have something called restriction and contraction, which is kind of like something in graphs. Like, I mean, in graphs, you can take a subgraph, right? Matroids, you have to be a little bit more careful if you take, like, let's say, some kind of a sub-matroid. You can't just start deleting independent sets or something, or deleting. You have to be a little bit more careful, but yeah, there are these concepts called restriction and contraction. So for a matroid, M, which is like xi, and a set S, which is a subset of X. The restriction of M to S is the matroid. Well, maybe I'll just say it's the pair. I mean, it's not clear that this is a matroid yet, but if you check the conditions, it's not hard to see that it is. So we'll write it as M with a line and then S. So that's the pair where the ground set is S. And the independent sets are all the independent sets of the original matroid such that Y is a subset of S. Okay. Okay, so this is like basically how you could take a matroid and get a smaller matroid by restricting to a set of a smaller set of points. This definition is going to come up. This one and the dual are going to come up in one of the proofs we're going to do in a little while. So, but yeah, it's not hard to see that this is actually a matroid because essentially this thing is going to inherit the properties from the original matroid. If you think of two sets Y and Z in this matroid, where Z is bigger than Y, well, these are still independent sets in the original matroid. So I can find something in Z that I can add to Y. But, I mean, so that just gives you the property, right? Okay. Another definition, which isn't going to really come up in the proofs, but it's worth knowing about, is contraction. So for a matroid M, equal to X comma I, and a set, an independent set, so a set Y in I. The contraction of M by Y is the matroid. Well, again, maybe I'll just say it's the pair, but it's going to be not too hard to see it's a matroid. So M, so we'll write this as like M kind of divided by Y in some sense. So it's like a slash, a diagonal slash. So it's going to be the pair where the ground set is like X take away Y. But now the set of independent sets is going to be a little bit different than above. So it's the set of all Z that was independent in the original matroid such that Y union Z is independent in the original matroid. Okay. So it's a slightly different kind of condition there. Have any of you guys heard of, in graph theory, graph minors? Like a minor of a graph? Okay, so then this analogy is not going to help, but so it's very, very strange that now I'm teaching you about minors. So this is related to matrix minors, or sorry, matroid minors. You're probably the first people in the world who have learned about matroid minors before knowing about graph minors. But essentially the point is that so the reason I'm mentioning graph minors, which I'll tell you what it is in a second, is that basically these contraction and restriction operations, if you think about them what they're doing in a graphic Matroid, it's the same thing as like deleting edges of a graph is like the restriction. And the retraction is like taking two edges of a graph and like, or taking an edge of the graph and like pulling the two vertices together. Okay, so yeah, so in graph minors, like, so a graph, let's say H, is a minor of a graph G if you can get H by starting with G and doing, and deleting some vertices and edges. So deleting vertices and edges would just give you a subgraph. So that's not, so there's something different here that I want to also be allowed to contract edges. So and contracting some edges, which means like taking an edge UV and like replacing it with just like pulling together those vertices and making it one vertex. So like the triangle, for example, is a minor of the 5 cycle. Right? Because if I just squish that edge, I get a triangle. Right? Because I can just go contract this edge, I get a 4 cycle, contract that edge, yeah, I get a triangle. Okay, so this is like the thing that, yeah, you might have seen before, but I know that you haven't. But basically, like, so this I think is a very simple idea to think about in graphs, right? You're just deleting edges, pulling edges together, and to make a new graph. So this is a very valuable concept in structural graph theory. Basically, if you want to show that a graph is kind of very complicated or something, you can find like a, you might want to show that it has a minor of a very complicated structure. Anyway, the point is here that if you think about what this is doing in terms of a graphic Matroid, so if I think about, okay, take a graphic Matroid for a certain graph, and let's say I delete an edge. Now, in the new Matroid, the new graphic Matroid, everything, yeah, every what do you call it, acyclic set of edges that doesn't include my deleted edge will be a what do you call an independent set in the new Matroid. I mean, that's exactly what's going on here. Think of S as being all the edges except for one, and I'm taking everything that was independent before, but doesn't include that edge I deleted. And somehow this is kind of related to contraction. So imagine I contract an edge, I just pull it together. So yeah, it's a little bit harder to see, but if I take let's say I take a spanning tree, for example, in the old graph, before I contracted the edge. It is a little bit hard to see, but this is the right condition. That this is how you're going to describe your spanning trees in the graph after I contract an edge. It's all the things that are spanning trees in the old graph, but that do not contain, or sorry, that I could add that edge to get a spanning forest in the old graph. Okay. All right. Okay, let's now talk about some equivalent axioms for matroids. Okay, so for the first theorem, we're going to have an equivalent definition of matroids in terms of the bases. So let X be a finite set. So I'm always going to just assume that every thing I deal with already satisfies the first two properties. These ones I'm going to think of as like not, like these are not really the interesting properties. It's really the third property that's like the interesting one. So we're always going to just assume everything satisfies these properties, and I want to get an equivalent form of this property. So the way I'll say this is I'll take I to be a subset of the power set, be a non-empty down set. Okay, so that's, if you think about it, that's going to imply that it satisfies these two things. So then what I want to show is that the following are all equivalent. So, okay, property A is the one I'm interested in, that xi is a matroid. Meaning that it satisfies property 3 over there. Right, because it already satisfies the first two. Oh, yeah, okay. Maybe before I do B, I meant to write this above, but I'll just write it here. So let script B be the maximal elements of I. So it's the collection of all maximal elements of I. So I want to show that so property A is equivalent to the following property, that for all B1 and B2 in B, and elements X, which is in B1 take away B2, there exists a Y in B2 minus B1 such that if I start with this set B1, I take away X, and then I add Y, this is also in curly B. Okay. So this is called like a basis exchange property. The idea is if I take two bases that are not the same, and if I take an element from the first one that's not in the second one, I could take B1, I could remove X, and then I could find something in B2 that I could add, and it'll stay like a basis. Okay. And the third property that's going to be equivalent to the other two, it's almost the same thing, but instead I want to take away, it's going to be the same thing, except this last thing is going to be different. I'm going to take B2, take away Y, union X is in B. So for all B1 and B2 in B, and X in B1 take away B2. So this part is not changing. I'm still picking X to be in the first set, not the second. And I'm still going to take Y from the second set, but not the first. But the conclusion is going to be slightly, very subtly different. The subtle difference is that I want B2 minus Y union X to be in B, in script B. Okay. And yeah, together these properties are kind of called the basis exchange axioms, right? You can take a basis, you can take something that's in the first, two bases, take something in the first, not the second, delete it, add something from the second, or you could take the second thing and, well, you can find something in the second thing I could delete and I could add the thing from the first one, right? You can kind of exchange elements between bases. Right, and if you kept doing this, if you kind of think about this, what would happen if I start with two bases that are very different, right? And I keep applying these exchange axioms, they're going to get more and more similar, right? I'm taking something, let's say, I'm taking something that's in the first one, not the second one. I'm taking it away, and I'm replacing it with something that's in the second one and not the first one. So I'm kind of making them more similar. You can kind of take two bases and kind of shift them to be one by one to become the same basis in some sense. Okay. So let's prove this. I have to say, none of these proofs for Matroids are super fun to do. Although I will say, next time and on next Monday, we're eventually leading to a theorem that's fantastic. Like it's absolutely beautiful and ridiculous that it's true. Yeah, right now it's kind of like you can't have dessert, right, until you've eaten your vegetables. We're eating a lot of vegetables today. So anyway. So what we're going to show is that, we're going to do this in, I guess, the sort of normal way. We're going to do A implies B implies C implies A. But I'm going to do this in maybe not this order. It's going to actually be kind of useful to do it in a different order. We'll see later on. So I'm going to prove C implies A first. So yeah, I'm assuming I've got this second basis exchange axiom that's true, and I'm going to prove that it's a matroid. But I already know the first two properties of a matroid hold, so I just need to prove that the third one holds. We're going to do this by contradiction. So suppose for contradiction, that there exists y and z in I such that y is smaller than z, and there does not exist some little z in big Z take away y, such that y union little z is independent. It's in I. So let's suppose it's not a matroid. Remember, the point of these basis axioms is they're useful because it allows you to start with two bases and move them to be closer to the same basis in some way. somehow this is intuitively like, so I'm gonna assume some condition here, which maybe is kind of related to that, right? So I'm gonna, among all such pairs, so we pick such a pair. Such that the intersection of y and z is maximized. Okay. So yeah, if there is such a pair, I can go through all of the pairs with that property and pick one with the biggest intersection among all of the possible pairs. And somehow like this idea of like taking bases and pushing them closer together is important, because what I'm going to do is basically take these sets y and z, find something where they're closer together, meaning a higher intersection, which also have that property, and that's going to be a contradiction. Okay. So y and z are independent. If you think about it, of course, since they're independent, I can find a maximal independent set that contains each of them. So I'm going to let B1 be and B2 be elements of B, script B. So these are maximal sets in I, such that Y is a subset of B1 and Z is a subset of B2. Okay. So yeah, just these things are in I. I can make maximal sets that are in I, so then they'll be in B. Okay. Any, is this clear so far? Okay. We haven't done too much, but yeah, okay. So, maybe I want to. Okay. I'm going to kind of divide this into cases, although case one's going to be really easy. But we have to consider it. It could happen. So suppose, like what would happen if y is a subset of B2? Okay. Well, the thing is, this can't really happen. Why? Well, here this downset condition is kind of important. So like B2 is in I. It's a maximal set in I. And I is like downward closed. And Y is a subset of B2, and so is Z. So like if I take Y union Z, that's a subset of B2. And B2 is, and kind of recall, I guess, like, so B2 is in B, but that means it's also in I, because it's a maximal set in I. But I is a downset, so then, like, so this is a subset of that, which is in I. So this is in I, because it's a subset of something in I. But then Y union little z is in I for every z in z minus y, because because I is a downset. Right, and there must be some such thing because z is bigger than y, right? So yeah, clearly, I mean, we chose these things so that no such z existed. So anyway, so that's a contradiction immediately. Okay, so the case 2 was kind of easy. Case 1 was easy. Case 2 is the one we need to think about. So y is not a subset of B2. Okay, z is, but y isn't. Okay. And somehow we need to use our basis exchange axiom. We have to use this C. But so what I'm going to do is just pick some, so that if it's not a subset, there must be an element of y that's not in B2. So pick x to be in y, take away B2. Okay. But this actually sets up this condition C quite well, because remember, y is a subset of B1, right? So x is in B1, take away B2. Because y is a subset of B1. So there exists some y in B2, take away B1, such that if I take B2, delete y, and union x, it's in B. So this is by property C, the thing that we're assuming. Right. Okay. So this little y, it can't be in big Y. It's not an element of big Y. The reason is because little y is not even in B1, and y is a subset of B1. So little y is not an element of y because y is a subset of B1. Okay. Here's what I'm going to do. I'm going to take, so like I said, remember we chose this y and z to be a counter, or like a, something that disproves the Matroid property, and we did it with this as big as possible. Now what I'm going to do is take my z and kind of move it closer to y. Like I'm going to take an element that was in z, delete it, and add an element that's in y, so that'll make them kind of more similar, and then I'm going to see what happens. So the kind of if you think of, it's hard to get any intuition about any of this, but if you see what's going on, like B2, take away y, add x, like we're going to do that, but with z, right? So I'm going to take z prime to be z. I'm going to take away y, and I'm going to add x. Okay. Remember where x came from. X came from y and not B2. So in particular, x is in y, and it's not in z, because z is a subset of B2. So basically what I've done here is I've taken my original z, I've added something that wasn't there before, but is in y. So I've kind of increased the intersection, and I've deleted this thing here. And so yeah, this will be like a subset of that thing. Okay. So definitely, like, z prime is still going to be bigger than y, because, if I delete this thing and I add something, it didn't get any smaller, because x wasn't in z to begin with. And if I look at the intersection of z prime and y, it's bigger than the intersection of z and y. Right, so this property is coming from the fact that our original sets, z was bigger than y, and this did not make this any smaller because x came from outside of z. Y, I don't know if y was in z or not, but I don't really care. At worst, this just got bigger, right? Okay, so Right. So now, since I made this bigger, since we chose this thing to be maximum at the start, we can find something in z prime minus y that I can add to y and stay independent. So there exists a little z in z prime take away y such that y union z is in I. And again, the reason for that is because this intersection is bigger than the original one. So the pair y, z prime cannot be a counterexample to the Matroid property because we picked the one with the biggest intersection. Okay. So now I'm going to claim, so we win if this little z is in z minus y, right? So so why is it in there? Let's see. So what I've got written here is that z prime take away y is a subset of z take away y. Ooh, drawing that backwards. Why? Because, I mean, what did I... yeah, if I delete x was in, the only thing that z prime has that z doesn't is x. But when I delete y, x was in y, so it just deletes the x anyway. So z prime take away y is a subset of z take away y. So therefore, since I found this z in there, it must also be in here. But then that contradicts the thing I started with, right? So there is a z in here such that y union little z is in I. Okay. So C implies A. All right. Which one are we going to do next? Okay, let's do A implies B. This one's the easiest one. Maybe I should have led with the easiest one. Let's see. Okay, let's do A implies B. Okay, we're assuming this thing is a Matroid. So we're assuming it satisfies that third property over there. So now I want to show that it satisfies B. So take two maximal independent set, or take two elements of B and take some x that's in B1 minus B2. Okay. So I want to find something in B2 that's not in B1 that I can add to B1 and keep it an element of B. Here's something we need to remember. So when I'm proving A implies B, we can assume at this point that that it's a Matroid. And what we proved, one thing we proved last time is if you have a Matroid, then all the bases have the same size. So since xi is a Matroid, all bases have the same size. I think I mentioned that last time, or maybe I even sort of told you the proof. I think it's also on your assignment. So, okay, so if all bases have the same size, so therefore, if I take B1 and remove x, and I take B2, these are both independent sets, and this one and the first one's smaller. Right, they're smaller because, yeah, B1 and B2 had the same size. I've now deleted something from this one. So now they don't have the same size and this one's smaller, right? And now actually my Matroid condition gives me exactly what I want. What I want is to find something in here that's not in not in B1, that I can add to this thing to make it independent, right? So by the third condition in the Matroid definition, there exists y in B2 minus B1 such that, in fact, I can make it even more precise. I can say it's in B2, well, oh no, yeah, sorry, I'll just write, well, technically what I get is this, but since x was not in B2, that's the same thing as B2 minus B1. So these are the same since x is not in B2. Okay, so I'm just applying the third condition there where z is B2 and y is this. And yeah, so technically I get, but it's the same as that because x is not in B2, such that B1 take away x union y is in I. Okay. Technically, this is not exactly what I wanted, though, right? In condition B over there, I want the final set. Like I've pretty much done it, but I want this to be in B, not in I. But can you see why it has to be in B? So what if it was in I, which means it's independent or whatever, but not maximal? Like, why would I get a contradiction? Yeah?
So something like it was maximal, you took something away, and you added something that wasn't in it, and so now it's the same size as it was.
Yeah, exactly. So yeah, just to kind of repeat that, so yeah, it started of a certain size. I took something away, I added something. It's the same size as it was before. And yeah, then it has to be maximal because, like I said, in a Matroid, all bases have the same size. So if it wasn't maximal, I could get an even bigger set, but then that's bigger than what I had before. It's not possible. So yeah, so that's exactly right. So, so since this set is the same size as B1, and all bases in a Matroid, have the same size, it must be maximal. So indeed, this thing is in B. Okay. Any questions about that? Okay. So now I want to prove the last thing is B implies C. This is slightly weird to do, but like these are the same thing basically, right? Except that like in the last line, it's just the B2 and the B1 are switched and the X and the Y are switched. Although that's kind of a signal to like that probably what's going on is really what you should be thinking about is start with your matroid, take the dual. Because like when you take the dual, everything goes kind of backwards. Like bases become sets that are disjoint from bases and like everything kind of switches. So in some sense, like this third condition C is kind of like a dual version of B. So what we're going to do is we're going to take the dual and like, but here's the thing, I haven't actually proven to you that dual matroids are matroids, so I have to be careful. I can't just assume it's a matroid. But anyway, so I'm gonna consider, so let's be very careful here, but so the dual, which is M star, so it's the pair X, I star. Well, okay, yeah. Okay, technically when I defined the dual, it was only for a matroid. Let's define, for any pair of xi, let's define the dual in the same way as before. So, but it may not be a matroid, right? So like, so I star is defined to be the set of all y, which is a subset of x, such that y intersect b is empty for some maximal, so for some b in B. Okay. So maybe I'm slightly wrong to call it the dual because I don't know, we're not assuming A anymore, so I don't know if M is a matroid, but anyway, I just define it in the same way. So let B star be the maximal elements of I star. But actually, like, these things are not that hard to define in terms of the elements of B, because, I mean, how could you have a thing that's maximal subject to being disjoint from some element of B? Like, if it's maximal with that property, it is the complement of B. I mean, or the complement of this kind of not curly B, right? So it's not hard to see, like, what is I star? It's just the set of all things of the form x take away B such that B is in curly B. Sorry, not I star, but B star. Right? Because if you wanted to have a maximal thing that is disjoint from some element of B, you would just take the complement. I mean, that's the biggest thing that's disjoint from a set. Okay. So we show that. So we first show, so I want to show that if M satisfies B, then it satisfies C. We're going to first show, so this is kind of a clever trick, actually. So that if M satisfies B, we're going to show if it's M satisfies B, then M star, or maybe I'll just say, sorry, if curly B satisfies B, then curly B star satisfies C. So that's not what we want to prove in general, but this is kind of going to be the first step. I mean, actually, this is most of the proof. Because here's the clever thing. So we are assuming, we're showing B implies C. We're assuming that script B satisfies the property B. We're going to use that to get that B star satisfies C. But here's the thing. We already proved that property C implies property A. So that's going to imply that, so if this satisfies C, then the dual is a matroid. But then we already proved A implies B. So then if B star satisfies C, it must satisfy property B because by taking that chain of implications. But if B star satisfies B now, then think of B as like the star of that. So then this one will satisfy C. Because like if this one satisfies B, then that one will satisfy, because if this one satisfies B, then that one satisfies C. So anyway, so this, there's a lot of B's and C's. But actually this is all, I mean, this is all we need to show. Because then, like, because we already know C implies A, and that A implies B. And also, if you think about it, B star is B. So like, this will imply that B satisfies property C. Okay. Maybe we don't need this condition anymore. I'll move over here. Actually, I'm going to run out of space there. Let's move back over here. I'll move over there in a second. So I'm assuming B satisfies property B. I'm going to show B star satisfies C. Where am I at here? So take two elements. Of B. Okay. So the only reason I'm taking these things is because, so I'm interested in B star at this point, but like, then if I take the complement of this and the complement of that, these are kind of two kind of generic elements of B star. So I'm going to work with these two things. I guess it's just useful to be able to reference things that are in B so that I can use the property for B. Okay. And let's take x to be in x minus b1, take away x minus b2, which, if you draw a Venn diagram and think about it, that's the same thing as taking x to be an element of b1, take away b2. I don't know why either, but if you draw the Venn diagram, you can probably somehow see it. Like, if this is b1 and b2, okay, I'm going to take the things that are outside of B1. Take away the things that are, wait, how does this work? So this would be x minus B1. And I'm going to take away the stuff. Yeah, maybe I've got it backwards. Take away the stuff that is outside of, that's not, what am I doing here? Yeah, take away this. Okay. So maybe this is that. Okay, so maybe I want to switch these around then. So let's switch this here. and here. Does this seem right? I don't know. It wasn't right before, right? And it's right now? Okay. Okay. Okay, so by property B, for script B, there exists some y in B2 take away B1 such that if I take B1, delete x, and I union with y, that's still in B. Okay. So therefore, just by the way that this B star is related to B, right? If something is in B, then its complement is in B star. So if I take x, take away B1, take away x, union y, that should be in B star. And then what is this going to be? It's like I take x and I throw away B1. Instead of like I should take away y and add x. Instead of, I should do the opposite of everything I just did, kind of. Oh, and I can also do a similar kind of way of representing this set, right? So this set here is x minus B1 minus x minus B2. So I started with something in here, B2 minus x minus B1. I found something that's in x minus B1 minus x minus B2 with the property that if I take this thing, oh, and this will be in B star. So if I take away, yeah. I think there's some weird thing about which one's my first set and which one's my second set, but like, yeah, I think this is the right way around to get, see. Don't. I think that like my x minus B2 is playing the role of B1 in statement C. Because I'm picking the x from, yeah, whatever the thing comes first when I pick the x is the thing that is the B1 over there. So yeah, this is playing the role of B. The thing is when you take complements, I mean, before when I had this as B2 minus B1, it was going to make a lot more sense. Obviously, it was wrong. But like now the 2s and 1s switch every time I do anything. But yeah, I pick a thing in here. Then I could find something in the other one, in the opposite direction thing, such that, yeah, now this is my second set is the x minus B1. Yeah. So I think that does it. And yeah, so this proves the whole thing because, like we said, once I know this satisfies C, it satisfies A, then it satisfies B, and then I can like do this in the reverse direction, and then I got B satisfies C. Okay, so yeah, that's the thing is now the good thing is once you've proven this once, you never have to think about. Well, I mean, you could just use these things, and you don't have to think about them, why they're true. Okay, so this was like the circuit axioms. Let me just, I'm not going to, obviously I've only got like 5 minutes or less, so I'm not going to prove anything else because the proof is similarly long. But there's also some axioms for circuits. So again, let X be a finite set. And let I be a non-empty down set. And let C be the minimal elements that are not in I. So then the following are all equivalent. So the first thing is that Xi is a matroid. The second condition, so yeah, you should be thinking of the collection C as the circuits in the matroid. So if you take two circuits, which are different, so such that C1 is not equal to C2, and I pick any Z which is in the intersection of the two. Okay. Of course, if they're disjoint, then there is no such Z. But I guess we're taking two distinct circuits that intersect. If you take anything in the intersection, then there exists a C3 such that C3 is a subset of C1 union C2, take away Z. Okay. Oh, this C3 is also in C. So yeah, if I take two circuits, delete something from their common intersection, I can find a circuit inside of that. Third property is kind of the same, except, yeah, so if C1, C2 are in C, I've got Z in their intersection, and I've got some X, which is in C2 but not C1. Then there exists a circuit, or there's C3 in C, with X being an element of C3 and C3, I don't know what that is. C3 is a subset of C1 union C2, take away Z. So like the third one is kind of like, it just seems like a lot stronger than the second one. Take two circuits, if I delete something from the intersection and fix an element in one of the circuits, I can find a circuit that contains that fixed element and is living inside the union minus Z. Maybe it's worth thinking about this quickly, about like what this kind of looks like in the setting of a graphic matroid. Right? Remember what a circuit in a graphic matroid is a cycle. So imagine I've got two cycles in a graph that intersect somewhere. Maybe they intersect a bunch of times. I don't know. Right? And if I take an edge in common, so this is my common edge, I delete it. This still has it still has cycles, so I can find a circuit inside of it. Even if I have, maybe the simplest picture is just drawing two cycles like this that just share one edge or something. If I delete that edge, I still got a cycle by going around like that. So So that's kind of the idea here. And yeah, these are all equivalent to each other. Okay, so it's 220. I don't think I had anything else interesting to say. I mean, this wasn't that interesting to say either. But yeah, there is something interesting coming up.